just have
Okay, yeah, I see what
But
you're
yeah,
saying.
that we need to figure that.
I mean, can we do
Interesting.
Yes.
old stuff that you would have would be things like virtual environments, full virtual machines,
Yeah.
right? Or you just don't virtualize that at all, right? So like, it's nothing. Okay? So the reason that this is required is because we have a lot of software that we're running, right? And when you're running software, software has to interact with hardware at some level. So at some level, you need to have the software interacting with hardware directly. And let's say that I have my machine that has a certain architecture, and you have your machine that has a different architecture, and I write software that runs on my machine. It doesn't guarantee that it's going to run on his machine, right? There are layers of abstraction that we need to put in place to do that. So what a container does, right? So let's go to what a container is. Or okay, actually, the better way to go about this is how we build a document. Can I use that eraser?
This is gonna be one for the ages.
So the reason that Docker came about is because we want to be able to run the same software on any computer and make sure that that software has all the resources that it needs to run, sort of tied up and wrapped in a little message, right? That's what the container is. It contains everything you need to run any of the software that you're running. Right? So when we say, okay, I want to create this Docker container, what does that mean? Well, first I need to define what that container will have in it, right? And so what I do is I create something called a Docker file.
So here's a question. F1.
So Docker file is sort of the first step in this process. Right? So when I define a Docker file defines the structure of the container and what the container will have in it, from something like what is its operating system, what architecture are we writing for, right? So if you remember back, you guys are familiar with like different architectures, right? So I have like x86 architecture versus I have ARM architecture.
Yeah.
What does that mean? Well, that means that my actual CPU has different instruction set architecture, ISA, and that's the hardware level description of what instructions are available to be run on that hardware. And so if I say, okay, I want my container to be a Linux and Ubuntu x86 container, what does that mean? Well, that means that everything that exists inside of that container will think that it's interacting with an x86 CPU that's running Ubuntu. Right? It doesn't matter if that container is running in something else. The container could be running in a Windows server off the shore of Guam. It doesn't matter. All the software will think it's running in an x86 environment in Ubuntu. Right? So that's what we define first of all. So you define that sort of overarching abstract concept. Right? So Docker file, key points is you have your architecture and your operating system. Right? That's like the base. Now, key thing for Docker files is this defines everything that's going to create what we call an image, right? So it's a second step.
That entire thing should just be taken off.
Right? So you can think of an image as
Why don't we just guess on and
so
wait, so this calculation.
So the image is exactly what it's a static representation of the container. If that makes sense. So before the container is running, the image defines in terms that Docker can understand what the container will do. So for a very simple example, let's say that I wanted to create an application. So what I use Docker for primarily is like servers. Right? So let's say I want to write a web server, and I want my web server to be able to run as soon as the container starts running, right? So what do I say? Well, in my Docker file, I say that I want my Docker file to be running off the Ubuntu 18.04 operating system on x86 architecture. So that way, that means that all of the software and binaries that I have in the container will need to be appropriate for that architecture. Right? So x86 binaries that are running in that container. And let's say that I'm using, I'm writing my web server, I have all my web server code, and this Docker file, or the Docker image container, will will be essentially an entire computer wrapped in a container, right? So that means it has a file system. That means that it has access to hardware resources abstractly. And so you also get to define in the Docker file what that file system looks like. Right? So what folders exist in your directory, what files are copied over locally. And I can show you like an example of exactly what that looks like later. But basically, what we have is this image is a compiled version of this Docker file. So I take the Docker file that's kind of like your source code, and you compile it down, you build it, what the key term is in Docker, is you build the Docker file into an image, and once you have an image, that's now a static representation of whatever container that you're going to spin up, right, or put up. The great thing about images is that you can share these, right? So if I want to say, I want to run my container on a distributed system, I want to run it on 7 different servers, and they're all across the globe. Well, then I have this image, and I pass this image around to the different servers, and those servers could be running different operating systems on different architectures. I could have a Windows XP server from like 1900s sitting over there. I can have like the latest Mac OS M1 server sitting over here. And this image, as long as Docker is installed on both of those servers, this image will be able to be spun up into a container on both those servers, right? All I pass around is the image. You don't necessarily need to pass around the Docker file, right? Because if you don't want to know, like, what exactly is going on, you have the binaries, it's kind of like packaging an executable and shipping it off so people can use it, right? So that's step 2. Step 3,
And then we'll have another, I think this is like.
We're getting this all documented.
we're switching colors because we're fun. Okay.
We're quirky like that.
Step 3 is what we call the container. So the image is
Having some munchies over there.
The way I was interpreting it was like this right here,
and this is static
one,
and this is what's running.
this,
The container is actually what's running. So when I take a Docker file to an image,
this is going to be
that's called a build.
this is.
When I take an image to a container, that's called
No, I
run.
know, but I said we could have
Okay.
used the Phillips.
So building takes a Docker file, which is like your source code for your image, and it compiles into an image that can then be distributed if necessary. Then you have this static image that exists on your local machine, and you can run it in Docker. So you can think of the actual application, Docker itself, is this virtualization software that handles all of the logic of taking whatever architecture you define here and actually running the code and transpiling and running it on your local machine or the server that you're running it on or whatever, right? So the version of Docker that you get for your machine will be specific to your local architecture. Then you can run any image on that local architecture through Docker, right? So you can think of it as a translator to an extent, right? So if you speak German and only German, but you're traveling the world and you're like trying to go on a food tour, culinary tour of the world and try everything, you take a translator with you, right? A polyglot. And everywhere you go, they're able to take the source, right? So if you go to America and speaking English, this guy knows English, and he is Docker, his name is Docker, and he translates English to German for you. You go to France, he translates the French to German for you. Anywhere you go. That's what Docker itself is actually doing, right? So once you define what you want your software to think it's looking at, then Docker handles actually making it do it on the actual machine. So that's the virtualization layer that exists. Okay. Another layer that we use is called Compose. Right? Remember Docker Compose?
Can I ask a question real quick?
Yeah.
So, like, why don't we use Docker for, like, all the other stuff? Like the telemetry system and...
So embedded systems don't need, so the drawback of something like this is performance, right? So if you think about latency, and if every time I have to say something to someone in a country that I'm not from, I have to go through a translator, right? So if I speak English and we're in Germany, I have to say a sentence. My translator has to process it, has to say a sentence. The German person has to process that, say a response. My translator has to translate it, and I have to receive it, right? So it's that extra layer of communication that's required. And it's a similar thing here for Docker, right? So you have higher response times, higher latency, which in embedded real-time systems is something that is sort of unacceptable. Right? So telemetry sitting board is a real-time embedded system. BPS, real-time embedded system.
Okay.
Control, same thing. So when you think about embedded systems, they're very much designing software for the exact hardware they're on, right? So there's, I guess we'll go to a little tangent here.
Fancy.
So when you have an embedded
Embedded.
system, there's something called the HAL, which is the hardware. I'm not gonna say that. The hardware abstraction layer, right? So the HAL is sort of like it's not virtualization. So I don't want to say it's like, but it's what allows us to write higher level software that interacts directly with hardware, right? So it only needs to go through the HAL. And so if I'm writing firmware for the STM32 microcontroller, that has its own like ARM architecture, versus if I have a different microcontroller that might have different architectures, I would have to have different HAL. So my software changes, right? So there's more work that's done up front in order to make sure that we're writing software for that hardware.
Okay.
Versus when we have something higher level where latency isn't as big of an issue, such as something like actual acquisition dashboard systems, not gathering data on the telemetry side, where we can allow for that, and in return, what we get is the ability to run this anywhere, and all that.
So like basically Docker is kind of like a sort of emulation layer
Yes.
that uses the image as like a sort of like the language you're trying to translate to, and then the Docker will be like written whatever programming or whatever for whatever system, like if it's on like a Linux machine or like if it's an X machine or something. ARM x86, someone out there made it for that thing, but from there it can just sort of emulate whatever the image says.
Exactly.
And it's all consistent, shareable.
So that's what we're doing.
I'm not sure why why would we need like a new container for like our test file?
A new container for your test file. So if we want to make sure, so the reason we would do something like that is if we want to run tests in an environment that we can control, right? So and we want to be able to sort of emulate the real application of where telemetry data can be used. We can define a container in our Docker file and create an image such that when we run that container, everything is very similar to the real world use case of that, right? So versus what we're doing now is sort of, I'm running it on my local machine, which is not what's going to actually be happening eventually. So there are some issues that could pop up once we make it to production, we call it production, that aren't popping up in testing, right? So like in like large scale software companies, what they have is they have like their production servers that you put your software on, but then when you're testing, the goal is to make your testing setup as similar to production as possible, right? So you don't want many differences. So that could be a use case. We can talk about more about exactly what we want to do with the testing thing, but that's sort of one.
Thank you.
Yeah, so compose, basically now we have an individual container, right? But what if I want many things running at once in conjunction with one another? The classic example for this is a web application. So a web application has a server and a client, and they need to interact with each other, right? So when you go to a website and it has an endpoint that's like, like it's a basic website like a calculator, right? Where I can add, subtract, multiply, divide. I press a button that sends, or I press some buttons and I write an equation, I press equals. Then that pings my backend, and my backend sends a response, and the client shows me the response. That's a simple example. But in that I have two major containers running. I have a client and a server. And so you can think of them as now you have like container A and container B. And they're both running on your machine. Now, the thing about these containers is by default, they don't know that each other exists, which is by design. Because they should, to themselves, they should seem like like they're the only computer, like they are the computer. Right? Like this is the computer that's running the software, and this is the computer that's running the software. They don't know by default that they're actually a virtualized machine in some other device that's running in conjunction with a bunch of other things, right? So we abstract that away first. But if you want them to communicate, you create what's called a network, which is, you define that in the compose file. So I'll go into like syntax in a bit, because it is new, but basically what that does is it creates this like bridge connection here. So that way they can communicate with one another. So to them, what it seems like is really what's happening is you have this, you have a local machine in which you have two containers that are running over a virtualized network, right? So from the perspective of me, the owner of this local machine who knows that that's what it is, this is what it looks like. But from the perspective of this, if I'm a piece of software running in container A, what do I think? I think I'm a computer, a physical device, and I'm literally existing over a local network. So think like if you have like an actual LAN with real computers. So from the perspective of containers A and B, that's what they think they are to each other. They think they are physical computers on a local network that are able to communicate with each other over that network, right? And so really that's what we're emulating, is we're emulating the fact that we have different computers that are able to communicate over a network instead of just containers running on one computer, right? Does that make sense? Okay. So that network bridge is what's happening there, and that's something you can define in Docker. So the key thing about Compose is that it's really just building on top of Docker. You can do all of this yourself, right? So if I wanted to do something like this, everything in the Compose file is just defined in YAML.
So Compose will run both of those containers.
So if you define it correctly, yes. But basically, Docker application that everything is running in. And so if I wanted to define something like this, I could do so without Compose. All I would do is I would make sure that I build both of those images, I would run both of those containers, and then there's a Docker command to create a network. I would make sure that I would run another command to make sure that both those containers are communicating over that network, and then they would be able to run a process.
So Compose just lets us like write out all that beforehand
And all
share
at
that
once.
configuration and save it.
Yeah, basically it lets you write the process in a markup language such that the compose binary will handle all of those steps for you. So you don't have to remember the commands and all that. And it's easy to visualize exactly. So YAML is just stand for yet another markup language. Say these networks defined as, and so what happens when you run like Docker Compose. Right, remember that command? Docker Compose up. Yes. Yeah. So that all that's doing is it makes sure all the resources are created. And once all the resources are created, it'll basically just run this command, and then any linking commands to link like the network or anything like that. But it's running basically this behind the scenes. And then if you were to do like so up is one command, build is another command. So you can also do Docker Compose build, which just does this step of it, and it won't actually spin up the containers. You can do both at once.
I think that's what we've been doing.
Yeah. So what you've been doing is doing both at once, and if it caches the build, and if the build nothing's changed, it doesn't rebuild, run it. So that's just the easiest thing to run. But basically, that's what's happening. Yeah. So the key thing is understanding how to define your image with the Docker file. Right? So basically, working one container at a time to define that. If you're only using a single container application, you don't need Compose, obviously. All you need to do is define a Docker file, compile it to the image, and then run it in the container. There's some helpful commands to like get into the container, because if it's another machine, you can like execute commands into that, like a shell session. So those are usually ways to debug. But in terms of like what Docker is and how to use it, this is This is pretty much it. Like, everything else is like.
Like, does that mean that we need a Docker file for every container we have?
Yeah, so every container has its own Docker file because that defines one container.
Because it seems like we only have one Docker file.
So I think we're actually using images that someone else already compiled for the other containers.
So that's
that-
another thing, right? If you have the image directly, then there does exist a Docker file somewhere for that, but you don't necessarily need it. So usually we get ours from it's called Docker Hub. It's GitHub for Docker images, so you can always pull an image from there, and so those are just the binaries. No one puts their Docker files on there. They only put their
So the one Docker file that we do have, is that for app?
It would be if you have any source code on your machine that you've written, which would probably be for app.
Yeah.
So what that does, if I had to guess, would be it. I haven't looked at it in a while, so I'm guessing, but
You want to
it'll copy. Yeah, it'll copy over like the source code. It'll have some base environments. Yeah, so it's some base environment. It'll install the requirements it has. It'll copy over the working directory, and then it'll run a command. So let's it's gonna be a bit of a pain to sell this up, but basically, yeah, this is a good example of exactly what we're talking about. So if you want to come here and point this out, but pretty much every Docker file that you write now will have some sort of base, right? And that's what the from is defined as. So here, there's some image called Python, and it's tagged as 3.9 Slim Buster, right? Which is just a smaller version of the Python 3.9 Docker image. So it's essentially saying, okay, there's this image that exists that has Python 3.9 installed, and that's what people use to execute Python. I'm going to take that image and I'm going to add a few things onto it. Right? So what am I going to do? Well, really what I'm going to do is I'm going to install GCC, which is new C compiler. I'm going to make a directory. So remember how I said that there's a whole file system that you can manipulate? So it makes a directory in the root called lhrpy. It's going to copy requirements. So when we're copying from local to image. Right? So think of them as two different machines. So I'm copying from local requirements.txt, which is here, and I copy that into this new directory. Right? And then I run the pip install on that requirements.txt. So that way, that's what's actually running in the server. I copy everything in my app directory, which is here, to here, right? And then, yeah, so I'm able to copy app from here, so that copies this entire directory with all my local source files there. It sets the working directory, which basically just means that once the container starts, that's where like the current working directory will exist. Right? That's what the current directory will be. It exposes a port. That's another thing that you can do. I mean, since we're networking, that's something we have to do. So if you think about the fact that like they're on a network, right? You have to expose a port on your network
Yeah, I
in
was
order
gonna
to access
ask
it.
like what the network is.
Yeah, so in here what we're doing is we're thinking of our machine as another machine on the same network as a container. And so if I want to be able to access something from my local machine that's in the container, I need to go through a port to do that.
Okay.
Right? So it exposes this port, and basically that's just some network configuration. So all of these are just things like commands that can be run on your local machine even, but they're just abstracted into this
So if
syntax.
we were to create a test file, we could just like expose that same port and it would connect over the network.
So if you're running the test file, it doesn't seem like you need to be able to access it. We'll see. So it wouldn't be the same port if you want to be doing both in conjunction, because they would clash. But yeah.
So it wouldn't interact the same way as the ones.
So this is a constantly running thing. It depends on what you want your test to do. If you want your test to be like one pass, like just does one thing and verifies something, you would need to. If you want to have the test actually do something with interacting with real devices in the real world, then yes, you would have to. But it would be similar to this. You just have some ports here. But the key thing is this is what's called like the entry point. So it's okay. Now I've basically created this machine from scratch. Right? I've like built this computer and I've installed all this stuff onto it. Now what does it do? Well, what it does is it runs this command. Right? So you can have a container where literally you just have like a Python script that's hello world, and all it does is print hello world. And you run your container and it'll just run and stop. Right? Containers aren't always continuously running applications. That's what they're typically used for, but it's not always the case. Now in this case, main.py just happens to be a continuously running script, right? So that's why it's happening that way. But main.py could be just a one-pass thing that just stops, and in that case, your container would just stop once that stops. So that's not always the case. Any other questions on this?
So if we were to add another container to the Docker Compose, would we have to start from making the Docker file and then like building it, running it, and then adding it to the Compose?
Yes. So you would make a new Docker file. It would have to exist in a different directory because Docker files there can be one Docker file per directory typically. Like, you can get around it, but it's easier if you do it that way. And then in the Compose file, you would essentially add in the services. You would have another service with the container name, whatever you want it. You would call the image. You'd give an image name, and then you would give a build. So here, this section here, you see how app is the only one that has a build? Because it's the only one that needs to be built from a source Docker file here. So it would be similar to this, where you have a build, you have context would be whatever directory that the new Docker file exists in. And then you wouldn't really need this, you wouldn't really need this. If you have an end file, you could use that. If you need to expose a port, you would do that. But really, I didn't go over this, actually, I should go over this. Go over volumes. But yeah, it would basically, you define builds, so that way when you run like Docker Compose build, the script looks at all the build sections and it runs those, right? So it'll build this Docker file. If you define another one in another directory, it'll build that Docker file and tag it with that image name, right? So
Can you say that again?
yeah. So if you have, let's say you have two services and they both have a build section, right? So the key things to define in the build section are the context, and you'll have the image name outside the build section, but that should also be defined. Right? So image names are important. So then what would happen when you would run Docker Compose build is it would scan through all the services. It would say, okay, here's a service. Does it have a build section? Yes. Where's the context? Okay, current working directory, because that's what period means. It's going to look for a Docker file in the current working directory, and it's going to run Docker build on that Docker file. And it's going to tag it with that image and tag. Then it's going to go to the next one, and it's going to do the same exact thing, right? And so if you look here, and you look at your list of Docker images, you'll see that you have one called data acquisition app, right? Which is what that name is, and it's tagged latest, right? So you notice you've never explicitly done that, but Docker Compose, when it built it, it found the Docker file that you were talking about and it tagged it with that name, and it exists now on your machine as an image. That binary is there. So the same thing would happen, but for the new image that you're wanting to create, the new Docker file.
So for context, right? Like, say we made another Docker file and it was like, I don't know, somewhere in this folder. Is that fine?
Well, you wouldn't want to make it an app because app is part like what you're copying over. You would want to make like a new directory.
Just a full circle.
Let's say you called a new directory and you called it like
Test
server, right? Then the context would be test server.
Okay.
And that's because that's where the Docker file exists.
Okay.
And so like once you run build once, it'll be there, and all you have to do is, like Tianu was saying, like start and stop.
Yeah, you just got to run the container.
Okay.
Now, if you Compose will handle that for you. You can always run the containers on their own. Like, no one's stopping you from doing that. So that's that. And then but the only key, like the thing is, like this is like a static representation, right? So if you ever change your Docker file, you'll need to rebuild because it won't be reflected. Now, key thing about volumes are cool, right? So you notice that the network was something with like networking and communication, right? Volumes are about persistent file storage. So you have like your volumes over here. Volumes are about files. So if you notice like something like here, right, you have source code and app. Now typically, like I said, an image is static, and the copying of app into the image happens at compile time, right? It happens while the Docker file is being built into the image. So if I have this set of source code, it would copy that in its current state over to the image. Let's say you push that image over to Docker Hub and someone else uses it. They would only be able to access what that state of source code would be, right? If you make an update of source code on your laptop, it's obviously not going to be reflected on their end, right? Because the image was already created, it was already compiled, nothing's going to be changed. But it can be annoying if like you're running your code in a container on your own machine, and every time you make one line of change, you have to like rebuild the image and rerun the image. Right? That'd be really hard. So that's what volumes are. Volumes basically are a link between you have your local file system and your container file system. So my local file system exists on my computer. My container file system also exists, like in physical storage, it's also on my computer because it's the only physical storage around. But in like abstraction, there's another computer like existing inside my computer that has its own file system.
In the calculation,
But if I make a change here, if this link wasn't here, there would be nothing there, right? So what happens is you create a volume that's essentially watching these changes. So it's watching these.
Start recording if you want.
And anytime a change is made here, it updates the container file system eventually.
The volume is doing it?
The volume is doing that.
Wait, the volume is a file.
Volume is not a file. Volume is like a structure,
Oh,
a Docker
and then in
structure.
your documents, you're like,
So the volume is a
It's like a file system.
it's a synchronization system, think of it like that, right? So if you've used like
I did something kind of weird.
I use Box Sync on my computer, so I have like cloud storage